bundled conductors. We have seen composite conductors and double circuit line. Now what is this bundled conductors? So this actually it is similar to the composite conductors in that it contains two or more conductors which are carrying the same phase current. But what happens in a bundled conductor is that the subconductors are not touching each other. Subconductors do not touch each other. Whereas in composite conductors, the subconductors are touching each other. Okay, so that is the basic difference. What about double circuit? How is it different from the bundled conductors? So double circuit is a kind of configuration. Okay, the double circuit, it is going to be something like this. Okay, so this is the transmission line, let us say. Now what happens is each of these conductors that we have here, it can consist of bundled conductors. That means it can have, let's say this is one bundled conductor. Here you have one bundled conductor. Okay, so like that a double circuit conductor can make use of bundled conductors. Okay, so this is double circuit three-phase transmission line using bundled conductors. You can draw here as well. All of these are bundled conductors. Now the next question is, why do we use bundled conductors and where do we use them? So this is used in extra high voltage applications. EHV means extra high voltage. And why they are used? So what happens in a bundled conductor, the effective geometric mean radiance is going to be increased, right? Because now instead of the conductors being close together, there is some gap introduced between the subconductors, right? So that means the effective geometric mean radius is going to increase. Now this is going to have multiple advantages. The first one is that the corona power loss is going to reduce. So we will learn more about corona losses, but if the effective diameter is increased, the effective GMR is increased, then the corona loss is going to reduce. And the second one is reduced radio interference, right? We have discussed what is radio interference. Voltages will be induced in the nearby communication lines, right? So that interference is going to get reduced. And finally, the inductance, right? The inductance is going to be reduced. So when the inductance is reduced, then inductive power losses are also going to reduce. Okay, so these are the advantages and we use them in extra high voltage lines. Now we will see some examples of these bundled conductor configurations. Okay, and we'll try to find out the GMR, the geometric mean radius. So first we can have two conductors which are combined to form a bundled conductor. Okay, so let's say this is one subconductor, this is another subconductor. The distance between these two is S, let us say. Okay, here what will be the GMR? This is equal to, first if you take this conductor, then the distance with itself, that means the radius R dash, and the distance with the second conductor into S, right? So here you have R dash S. Similarly, you have for this conductor the distance with itself and this distance. So you are going to have another S R dash to the power 1 by 4. Okay, just like we have calculated for the double circuit line. In a similar manner, we are going to find out the GMR here. So what will this be? This is R dash S root over to the power 1 by 2. Okay. Next, let us say we take a 3 subconductor configuration. This distance is S, S and S. Here what will be the GMR? This is going to be, if you take one conductor, the radius into this distance into the other distance. So you have R dash into S into S. Similarly, you have for this repeats for all the 3 conductors, right? So to the power 3, and since there will be 9 number of terms, you can write to the power 1 by 9. So you are going to get r dash into s to the power 1 by 3. And similarly, if you take 4 conductors configuration, each of this distance, let us take as s. Then here what will be the GMR? If you see here in the first case, r dash into s to the power 1 by 2, right? So for 2 conductor configuration, the radius into the distance with the other conductor to the power of 1 by how many ever conductors are present. Similarly, in the second case also you can see the radius r dash, distance with first conductor, distance with second conductor to the power 1 by 3. In a similar manner, we can write for 4 conductors as well. How? The radius, distance from this conductor S to this conductor S, and this conductor is going to be root 2s, right? So this is going to be r dash into s into root 2s to the power 1 by 4, because there are 4 conductors. Okay, so this is how you can find out the GMR, the geometric mean radius of bundled conductor arrangements.